Every time an AI agent retrieves a memory, finds a relevant document, or runs a RAG query, there's a vector database doing the heavy lifting underneath. It's the silent foundation of modern agentic AI. Today, what embeddings actually are, how similarity search works under the hood, and which vector database to pick for your project. Let's start at the bottom of the stack. Begin with embeddings. An embedding model takes any chunk of text and outputs a long list of numbers, a vector. It might be 384 dimensions, 768, or even 1,500 dimensions depending on the model. The exact count varies. The crucial property of embeddings is this: similar meanings produce vectors that are close together in that high-dimensional space. The phrase dog, the phrase puppy, and the phrase canine all land near each other. The phrase Python and the phrase JavaScript land near each other on a different axis. The phrases invoice and receipt land somewhere else entirely. Once meaning is encoded as geometry, search becomes math. Embed the user's question into a vector. Find the K vectors closest to it in the database. Return those chunks of text. That's the entire similarity search algorithm, beautifully simple. Distance between vectors is usually measured with cosine similarity, basically, the angle between two vectors in space. Vectors pointing in similar directions get high cosine similarity scores. Vectors pointing in different directions get low scores. The reason this is so powerful is the user can ask their question in any wording, synonyms, paraphrases, even different languages, and similarity search still finds the right content. Keyword search would miss it. Vectors don't. So why do we need a special database for vectors? Why not just store them in Postgres and call it a day? Because comparing your query vector against a million stored vectors brute force takes too long. Hundreds of milliseconds at best, sometimes seconds. That's not viable for an interactive application. Vector databases use approximate nearest neighbor indexes, algorithms with names like HNSW and IVF, to answer in single-digit milliseconds with near-perfect recall. They sacrifice a tiny bit of accuracy for huge gains in speed. They also handle live updates without rebuilding the entire index, support hybrid search combining vectors with metadata filters, and scale to billions of vectors when needed. Now, which vector database should you actually use? 5 serious options. Pinecone is the premium managed service. Set it up in minutes, pay for uptime and scale. You don't operate anything. Weaviate is open source with strong hybrid search built in. You can self-host or use their managed offering. Particularly good when you need both vector and structured search together. PVector turns Postgres itself into a vector database. Add an extension, you have a vector store. Often enough for hundreds of thousands of vectors, and your data stays in one place, your existing Postgres. Pdrant is a fast Rust-based open-source option. Excellent for self-hosted production. Strong filtering and snappy performance. Chroma is lightweight and embedded, ideal for prototyping and small datasets. Runs in process with your Python application. My honest take after using several: try PVector first if you're already on Postgres. Graduate to a dedicated vector database only when you outgrow it. Most projects never do. 5 rules of thumb that save you pain in production. 1. Pick your embedding dimensions wisely. Bigger embeddings give slightly better quality but use more storage and slow searches. 1024 dimensions is a great default for most use cases. 2. Re-embed when you change models. Vectors from one embedding model can't be compared with another's. The math doesn't transfer. Plan for migrations. 3. Always store metadata alongside your vectors. Source, date, author, access controls. You will need them for filtering and security. 4. Apply security filters before similarity search, not after. Tenant ID, user ACLs, these need to be enforced at query time. Don't leak data across customers because the agent helpfully retrieved it. 5. Monitor recall on a labeled set. Bad agent answers are usually bad retrieval. If recall drops on your golden set, you have a problem. Meaning, made searchable.